Dear friends, today we learn CMOS inverter part 2. Part. In CMOS inverter part 1, we have analyzed different pull-up network. At the end, we have a conclude CMOS inverter have a zero static power dissipation and it's have a strong zero out. So CMOS inverter have a two greatest advantage. One is advantage of CMOS inverter. One is 0 tends to 0 static power dissipation. And another advantage of CMOS inverter is it's have a strong logic zero, strong zero output, right? So CMOS inverter it is widely used device to implement any digital logic. So CMOS inverter it's have a pMOSFET which is which is work as a pull-up device. So this is a pMOSFET and this is a source terminal of pMOSFET. It is connected at VDD. Bulk terminal of pMOSFET is also connected at VDD. So there is no any source to bulk voltage. So substrate bias effect is zero. Gate terminal of the pMOSFET and the gate terminal of nMOSFET is connected at input and the drain terminal of pMOSFET and the drain terminal of nMOSFET is connected at out, which have the load capacitor, and the gate of nMOSFET and gate of pMOSFET is connected at input, and the bulk and the source terminal of nMOSFET is connected at ground. So this is CMOS inverter circuit. Now here we can see the gate to source voltage for pMOS, it is equal to gate of pMOS it connected at input and source of pMOSFET is connected at VDD. So gate to source voltage of pMOSFET is V in minus VDD. Similarly, drain to source voltage of pMOSFET it is equal to drain terminal of pMOSFET it's connected at V out and source terminal of pMOSFET it connected at VDD. So drain to source voltage of pMOSFET it is V out minus VDD. Similarly for the nMOSFET. So gate to source voltage of nMOSFET it is equal to gate terminal of nMOSFET connected at VDD V input sorry and the source terminal of nMOSFET is connected at ground. So gate to source voltage of nMOSFET it is V in minus 0. So it is V. Similarly drain to source voltage of n MOSFET, pull down device. N MOSFET work as a pull down device. P MOSFET it is a pull up. So drain of n MOSFET is connected at out, and the source of n MOSFET is connected at ground. So drain to source voltage of n MOSFET is V out minus 0. So it is a V out. Right? Now here we want to analyze a noise margin of a CMOS inverter. So to analyze the noise margin, here we can see whatever the drain current of P MOSFET, it is equal to the drain current of N MOSFET, right? So drain current of P MOSFET, it is equal to the drain current of N MOSFET. So to find out the operating region of P MOSFET and N MOSFET to derive the critical voltage, so let me quickly revised condition for the operating region of MOSFET and the condition for the operating region of nMOS. So for we know for the P MOSFET, right, when when the gate to source voltage of P MOSFET, if it's greater than the threshold voltage of P MOSFET. Threshold voltage of P MOSFET for enhancement device, it is a negative voltage. Suppose let for the example here we'll take, suppose it is a 1 volt, right? So whenever the gate to source voltage of P MOSFET, if it's greater than the VTP, means the negative voltage of the negative threshold voltage of P MOSFET, then P MOSFET operate in a cutoff region. Then P MOSFET operate in a cutoff region. So P MOSFET operate in a cutoff region. For the cutoff region ID current is equal to 0. Now when gate to source voltage of P MOSFET, if it's less than equal to the threshold of P MOSFET, is a negative voltage. So whenever the gate to source voltage of P MOSFET is more negative compared to the threshold voltage, then it's either operate in a linear region or a saturation. So condition for the linear region is whenever the gate to source voltage of P MOSFET minus its threshold voltage, if it's less than the less than equal to the drain to source voltage of P MOSFET, then it is operate in a linear region. And in linear region, ID, we know it is very well, it is a Kp by 2 into 2 times of VGS of P minus VTP into VDS of P minus VDS of P no square, right? And when the VGS of P minus VTP, if it's greater than the VDS of P, then it is operate in a saturation. And in saturation region, ID current is defined as Kp by 2 into VGS of P minus VTP whole raised to, right? So let me continue for the nMOS. So for the nMOSFET, whenever the VGS of n, if it's less than the threshold of nMOSFET, nMOSFET threshold is some positive value, then it is operate in a cutoff region. And in cutoff region, we know ID of n in cutoff is equal to 0. Whenever the VGS of n, if it's greater than equal to VT of n, then it's either operate in linear region or a saturation. For the linear region, condition is VGS of n minus VT of n. If it's greater than equal to VDS of n, then it is operate in a linear region, and we know the linear ID current is defined as transconductance Kn by 2 into 2 times of VGS of n minus V of n into VDS of n minus VDS of n square. Similarly, whenever the VGS of n minus VT of n, if it's less than the output VDS of n, then it's operate in a saturation. And for the saturation region, ID current is defined as Kn by 2 into VGS of n minus VT of n square, right? So now let identify operating region at different input voltage. So we know the transfer curve VTC of an inverter, voltage transfer characteristics. It's have a input voltage versus out. Now for the CMOS inverter, output have a strong zero, so it goes up to the zero voltage. So it is VDD. Here the voltage at which the output goes zero, it is a VDD plus threshold of VTP, magnitude of threshold of VDD plus VTP, not a magnitude, is a VTP. So this voltage is VDD plus VTP, and VTP is negative. So suppose VDD is 5 volt, then VTP is suppose minus 1 volt, then it is 4 volt. So whenever the input is greater than 4, then it is goes into the P MOSFET goes into the cutoff. Let me now two more points here. When the maximum output is defined as a VOH and minimum output defined as VOL, right? And the another 2 point in the VTC, when dV out divided by dV in is equal to -1, corresponding input voltage is called a VIL. And similarly, at a higher input voltage, when again we'll get the slope of this curve is -1, corresponding input voltage is called a VIH. And whenever the input and output is equal, at this point, corresponding input and output voltage is called a switching threshold, VTH. VTH, right? So let me find the VOH, VOL, VIL, VIH, and VTH of the CMOS inverter, right? So let one by one, before finding, we need to find out the operating region of nMOS and pMOS. So to let find the operating region at a different voltage, right? So the operating region, let me find for here somewhere here have a threshold voltage of n MOSFET. Threshold voltage of the n MOSFET is near about what. For more simplified, let's take different values, right? Then you will get the better idea, right? So suppose VDD is 5 volt, then then Vt of n, suppose it is positive, it will be near about +1. VIL is near about the suppose 2 volt. VTH, it is for ideal it is 2.5 volt. VIH, it is suppose 3.5 volt. Then VDD plus VTP, it is 4 volt. VTP, it's -1 volt. So different values, so you can realize very easily, right, if you have some value. So in this we can see, from this we can see VDD, it is VDD is a greatest value. Then have the VDD plus VTP, then have the VIH, then have the VTH, then have the VIL, then have the VTN, and so this is the relationship of a different critical voltage of any VTC, of any VTC, right? So from this, let we find operating region at a different input voltage. So if you want to, let me prepare one table: V input voltage, V output voltage, operating region of an nMOS, and operating region of MOS. So let's find the for the suppose if you want to derive the VOH, then VOH is the maximum output voltage, and it is output voltage. So when the output is VOH for any VTC, input is less than the, means n MOSFET operating cutoff, and it is less than the threshold of n MOSFET, right? So when input is less than the threshold of n MOSFET, here we can see when input is less than threshold voltage, will get the maximum output, right? So first condition is input is less than the threshold of n MOSFET. In that case, we'll get the maximum output, and it is. Now what is operating region? So here itself says the input is less than the threshold of n MOSFET. So the threshold of n MOSFET, VGS, right? So here input is less than the threshold of n MOSFET, near about 0, and output is output is VOH maximum, right? So from this, let's derive the operating condition. So let me first check for the PMOS. What is operating region of PMOS? Is it operate in conducting or it is in cutoff? Let me check. So let me check first for the its VGS of P. Is it greater than or less than the threshold of uh, P MOSFET or not, right? So let me check if it's less than the threshold of N MOSFET or not for the conducting, right? So let me substitute the VGS of P in terms of input and output voltage. So what is the VGS of P? So we already derived the VGS of P. It is input minus VD, right? Is it less than the threshold of P MOSFET or not? We have to check. Now, what is the input for this condition? Input is near about 0. What is the VDD for our example? It is, let's say, 5, and VTP is near about -1. So minus 5 is less than equal to -1 means this condition is correct. It is satisfied, right? So this condition is satisfied. That means P MOSFET operate in either linear or saturation. It is in conducting state. So P MOSFET operate either linear or a saturation region. Now we have to identify is it operate in linear or saturation. For that, let we for the linear region, we know the whenever the VGS of P minus VT of P, if it's less than the VDS of P, then it is operating linear region. So let's substitute the VGS of P and VDS of P in terms of input and output. So what is the VGS of P? It is a input voltage minus VDD minus VTP as it is. Is it less than equal to VDS of P? Let's substitute the VGS of P in terms of input and output voltage. It is a Vout minus. So VDD cancel from the both the side minus VDD. So our equation is V in minus VTP. Is it less than equal to Vout? Let's substitute the value of input and output. So input in this case is 0 VTP and output in this case is VOH for a VDD, right? So here minus 1, is it less than equal to 5? VOH is maximum output voltage and it is a 5 volt. Is VDD is 5, so maximum output voltage is 5 volt. So is it this plus 1 is less than equal to 5? Yes, plus 1 is less than equal to 5. No, sorry. Here VGSOP, it is the yes, and VDSOP, yes. So this condition is satisfied. That means a P MOSFET operate in a linear. P MOSFET is operating in a linear region. So let's substitute the P MOSFET is operating in a linear region. Right? What about the nMOS? So let me check for the nMOSFET. So for the nMOSFET, let me check is it in operate in a conducting or it is in a cutoff. So for that, let's check it is in conducting or in cutoff. So whenever VGS of n, if it's greater than equal to VT of n, then it is operating in conduct. Let's check this condition is satisfied or not. If it not satisfied, that means it is operating in cutoff. If it's satisfied this condition, that means it is operating in a conducting stage, either in a linear region or a saturation. So let's substitute the VGS of n in terms of input. It is input, and here it is n VT of n as it is. Now what is input in our this case is 0 and the VT of n is near about 1. So this is not correct. This is not satisfied. 0 is not greater than equal to 1. So that means this condition is not satisfied. That means VGS of n is less than the VT of n. And once the VGS of n is less than the VT of n, it is a nMOSFET operate in a cutoff regions, right? So nMOSFET is operating in a cutoff region. So here we have to write nMOSFET operating cutoff. Is it clear? Now let's find for the another critical voltage what is the operating region, right? So let's see in a characteristics, right? VTC. Let we find the operating region for the VIL. Let we find the operating region for the VIL, right? So when we want to derive the VIL at that time, what is the operating region of nMOSFET and what is the operating region of PMOS? So let's see, when input is a VIL which is greater than the threshold of n MOSFETs. VIL is greater than the threshold of n MOSFETs, right? And it is logic 0 input, so it produced the output is near about the logic 1. Output is near about the VOH. Output is near about the logic 1. So let's derive the condition of n MOSFET and p MOSFET in this case. So when input is greater than the threshold of n MOSFET, but it is a VIL. So when input is greater than the threshold of n MOSFET and it is a VIL, at that time what should be the output? Output should still high or near about VOH. Output is high near about the VOH because input is VIL which is the logic 0 input. So it produces the output is logic 1. Right? Now our step is to find out the operating region. So definitely input is, let's find the operating region of P MOSFET first and then we'll find for N. Now let's check for the P MOSFET is operating conducting or not. So for whenever the VGS of P, if it is less than the threshold of P, then it's operating in a conducting region, right? So let's substitute the VGS of P in terms of input. So it is input minus VDD. Is it less than equal to VTP or not? We have to. Then input is VIL minus VDD. Is it less than equal to VTP or not? So this factor is more negative compared to the VTP, right? So this is satisfied. If we substitute different value, so 2 minus 5, is it less than minus 1? Yes. Yes, this condition is set. That means the P MOSFET operating in a conducting stage, either in a linear region, this condition is satisfied, so it is operate either in linear or in saturation. Let's check for the linear region. For the linear region, condition is whenever the VGS of P minus VTP, if it's less than equal to VDS of P, then it is operate in a linear region. So let's substitute the VGS and VDS in terms of input and output voltage. So VGS of N, the P, it is input minus VDD minus VTP less than equal to Vout minus VDD. So VDD cancel. So here it is input minus VTP. Is it less than equal to Vout? Right. So input is VIL, VTP is VTP, and Vout is near about the VOH. Right. Let me check. So let me substitute the value. Is it less than equal to VOH, which is the 5 volt? So here 2 plus 3 is 3 less than equal to 5. This condition is satisfied. That means P MOSFET operate in a linear region, right? So whenever Vin is equal to VIL, P MOSFET operate in a linear region. It is continue operate in a linear region. Okay? So whenever the input is logic 0, at that time P MOSFET operating in a linear region. Now let's check for the nMOSFETs. Let me check for the nMOSFET. Let me check is it operate in a conducting or not. So for that VGS of N Is it greater than equal to Vt of n for the conducting? If it's greater than, then it either operate linear or saturation. So Vgs of n, it is a input voltage, and Vt of n, and input here it is a VIL. Yes, so VIL is, let if we take the value, then 2, then 2 is greater than the 1. So this is satisfied, this is satisfied. That means nMOSFET operate either in linear or in saturation regions. For the linear region, condition is VGS of n minus VT of n. If it's greater than equal to VDS of n, then it's operate in a linear region. Let's substitute the value of VGS of n. It is input minus VT of n. Is it greater than the V out? So input here it is VIL minus VT of n. It is greater than the VOH. Here it not greater than the VOH, because if we substitute the value, then also 1 is not greater than equal to 5. So this condition is not satisfied. So this condition is not true. So this condition is not true means nMOSFET not in a linear region. So what is the nMOSFET operate in a saturation region? So when input is equal to VIL, nMOSFET operate in a saturation region. Okay. Now let's take the, for when input and output is equal for this VTH, what is the operating region of nMOSFET? And so when input and output is equal and it is equal to VTH, at that time what is the operating region? So when input is equal to VTH, at that time output is also equal to VTH, because input and output is equal. So input is also VTH, output is also VTH. So input and output is equal. So in that case, input and output is equal. So input is greater than the threshold of nMOSFET. So nMOSFET is operate either linear or saturation, and pMOSFET is also operate either linear or saturation. So let me step by step check for the first pMOSFET. Right? So for the pMOSFET, let me check is it in a conducting or not. So for the conducting, this condition must be satisfied. So let's say input minus VDD, is it less than equal to VTP or not? Input is here, it is a VTH minus VDD, is it less than equal to VTP or not? Let's put the value, so you'll get the greater idea. So VTS is 2.5, VDD is 5, and VTN is -1. So minus 2.5 is less than the -1. This condition is satisfied. That means pMOSFET operate in a conducting stage, either linear or a saturation. Right? For the linear region, condition is whenever the VGS of P minus VT of P, if it's less than equal to VDS of P, then it's operate in a linear region. Let's substitute the VGS of P. It is a input minus VDD minus VTP, and VDS of P, it is a output minus VDD. So what is the input minus VDD? Input minus input is VTH minus VDD minus VTP. Is it less than V out is also VTH, right? So VTH cancel, VDD cancel. So minus VTP, is it less than equal to 0? What is the value of minus VGP? VTP is -1, so minus minus plus 1. So it is +1 is less than equal to 0. Not. +1 is not less than equal to 0. So that means this condition is not satisfied. That means pMOSFET is not in a linear region. Right? So pMOSFET operate in a saturation region. So let's put the value pMOSFET operate in a saturation region. So whenever input and output is equal, at that time pMOSFET operate in a saturation region. Now let's check for the nMOSFET. When input and output is equal, it is equal to VTH. At that time, what is the operating region of nMOSFET? So let me check, it is in a conducting? Definitely it is in conducting, because input is greater than the VT of n. So for the conducting Vt of n, so Vgs of n is equal to input. So input is equal to Vth, and Vth, let's substitute the value. It is 2.5 greater than plus 1. This condition is satisfied. This condition is satisfied. That means nMOS operate in either linear or saturation. So for the linear region, condition is whenever the VGS of n minus VT of n, if it's greater than equal to VDS of n, then it is operate in a linear region. So let me check this condition is satisfied or not. So VGS of n, it is equal to input, and VDS of n, it is equal to output. Input here it is a VTH, and output is also a VTH. So it is cancelled. So minus 1 is greater than equal to 0? Not. Minus 1 is not greater than equal to 0. So this condition is not satisfied. That means the nMOS is not in a linear region. So nMOS operate in a saturation region. So whenever the input and output both are equal, then both the MOSFET operate in a saturation regions. Right? Now let's find operating region when the input is equal to the VIH. When let we continuously increase the input. So when input is equal to VIH, VIH is the logic 1 input and it produces the output near about 0. Output is near about 0. Logic 0. Right? So let find the operating region when input is equal to VIH. When input is equal to VIH, output is, what about the output? So output is near about the low. Right? So let's find the operating region for nMOS and pMOS in that case. So let me find first the for the pMOS. So let me check is it in a conducting or not. So for that VGS of n, is it less than the VT of P or not? So VGS of P, it is a V input minus VDD. Is it less than the VT of P? So input is a VIH minus VDD. Is it less than the VTP or not? Let's substitute the value. Suppose 3.5 minus 5 is less than the minus 1 or not. So minus 1.5 less than minus 1, not. This condition is not satisfied. Yes, this condition is satisfied. Sorry, this condition is satisfied. That means the pMOSFET is this condition is satisfied. That means pMOSFET operate either in linear or in a saturation. So for the linear region, condition is VGS of P minus VT of P. Is it less than equal to VDS of P or not? So VGS of P, it is the input minus VDD minus VTP. Is it less than equal to Vout minus VDD or not? Let VDD cancel. So input is equal to VIH minus VTP. Is it less than equal to the low? Output is low, near about 0. Uh, let's say low, right? So let's substitute the value here. The 3.5 minus 1 is less than equal to low or no, near about 0. So 3.5 plus 1, 4.5 is not less than equal to 0, right? So it not operate in a linear region. So pMOSFET is continuously operate in a saturation. So in short, when input is logic 1, pMOSFET in operate in a linear region. Input is logic 0, pMOSFET operate in a input is logic 1, pMOSFET in saturation. Input is logic 0, pMOSFET in a linear region. Right? Now let's find about the nMOSFET. What is the operating region of nMOSFET? Right? So for the nMOSFET, let we check for the conducting stage. Whenever the nMOSFET is greater than equal to VT of n, so input is greater than equal to VT of n is or not. Input is VIH is greater than the VT of n or not. Yes, because it is 3.5 in 1, so it is satisfied. That means it is in conducting stage, either linear or in saturation. So let's check for first the linear region condition. If it's not in linear, then it's in saturation. If it's in linear region condition is satisfied, that means it is operating in a linear region. So let me check the condition for the linear region, right? So whenever the VGS of its input, is it greater than equal to output or not? So input is a VIH, is it output is low? So VIH is near about 3.5, so 2.5 greater than equal to low, greater than 0, so it's satisfied. This condition is satisfied. That means it's operating in a linear region. Okay? So nMOSFET operate in a linear region. Okay? Now let's find the operating region when the input is greater than the VDD plus VDD. At that time output is low, output is tends to 0. Let's find the operating region when input is equal to greater than equal to VDD plus VDD. Output is low, tends to 0, right? So let me find the operating region of nMOSFET and pMOSFET. So let me first find for the pMOSFET. What is the operating region of pMOSFET? So for pMOSFET, is it conducting when VGS of P if it's less than equal to VT of P? So what is the VGS of P? It is the input minus VDD. It is the VGS of P. Is it less than equal to VTP? Input here it is a greater than VDD plus VTP minus VDD. Is it less than equal to VTP? This is greater than that, right? So this value is not exactly but greater than that. So that means this condition is this is greater than that. That means this condition is not satisfied. That means it is not in a linear region. Linear it is it operate in a cutoff region. So that means VGS of P it greater than the VT of P. So this condition is for the cutoff region of pMOS. So pMOSFET goes into cutoff when the input is greater than VDD plus VTP. So when input goes greater than the VDD plus VTP, pMOSFET goes into the cutoff region, right? And it will make the output strong 0. So this is the region. The pull-up device goes into the cutoff region and it will make the strong 0 output, right? So in this case here pull-up device goes into the cutoff region. If you see any other inverter circuits, resistive pull-up network circuit, depletion load pull-up network circuit, right? Enhancement load pull-up network circuit. In any inverter circuit, pull-up network never goes into the cutoff. That's why we never get the VOL tends to 0, means strong 0 out. In the case of CMOS inverter, in the circuit where the pull-up network goes into the cutoff when input is VDD plus VTP, right? So at that time we'll get the output is goes into the 0. We'll get exact 0 out. Pull-up network device resistance is uh, infinite and pull down network resistance is low, so we'll get output can goes up to the capacitor can discharge up to the. Let me find the operating region when input is greater than VDD plus VTP. So VGS from is it greater than equal to VTN or not? So input is greater than equal to VTN or not. So input here is VDD plus VTP or greater than that. Is it greater than VTO of not? So 5 minus 1 is greater than 1. Yes, this condition is satisfied. This condition is satisfied. That means the nMOSFET either operate in linear or operate in a saturation regions. So let me find the is it operating in a linear or saturation. So VGS of n is greater than VT of n is greater than the VDS of n or not. So VGS of n, it is a input minus VT of n is greater than the output. So out. So input here it is a VDD plus VTP minus VT, and at that time when input is greater than VDD plus VTP, at that time output is 0, goes to 0. So 5 minus 1 plus 1 is greater than 0. Yes, this condition is satisfied. That means nMOSFET is operating in a linear region. So let's substitute the nMOSFET operating in a linear, right? So this is the operating region of nMOSFET and pMOSFET at a different critical voltage. Let me summarize this in a VTC curve at a different region. What is the operating region of nMOS and pMOS? So whenever our input is less than the VT of n, let me call this region as region A. So in A region, when input is less than the VT of n, at that time nMOSFET operate in a cutoff and pMOSFET operate in a linear region. Right? Now pMOSFET operate in a linear region. Now when the input is greater than VT of n and less than, suppose the input in this range, let me draw with different color. So if our input is in between this range, greater than VT of n and less than the threshold VTH, in this range, let me call this is B range. In this range, nMOSFET operate in a linear region, and the nMOSFET operate in a saturation region, and pMOSFET operate in a linear region. Right? Now when input and output is equal at this point, at the point when input and output equal, let me call this point as a C. So when input and output is equal, at that time both the MOSFET are operating in a saturation. Now for the when the input is greater than the threshold VTH and up to the VDD plus VTP, in this range, let me call D. In this range of input, when input is greater than VTP up to the VDD plus VTP, this range of input, in this range of input, nMOSFET operate in a linear, nMOSFET operate in a linear, and the pMOSFET operate in a saturation. Now when input is greater than the VDD plus VTP and up to the VDD, in this region, pMOSFET operate in cutoff and nMOSFET continuously operate in a linear. So I have the 5 different region. One is the region A, when the range of input is 0 to VTN. When our input range is 0 to VTN, at that time nMOSFET operate in a cutoff, and the pMOSFET operate in a linear region. Now for the B operating region, it is the range of input voltage greater than VT of n and less than the VTH threshold. So when input voltage range it's greater than the Vt of n up to the Vth in this region. When input is range from greater than Vt of n up to the Vth in this region, nMOSFET operate in a saturation region and pMOSFET operate in a linear. In a C, when input and output is equal, when input is equal to Vth at single input range, at the single input it not range at single value, when input is Vth, nMOS and pMOS both are operating in saturation. In fourth condition, fourth region, when input is greater than the switching threshold but less than the VDD plus VTP. At that time, nMOSFET is operating linear and pMOSFET continuously operate in a saturation. And in last region, E region, in that case, if our input is greater than VDD plus VTP, input is greater than VDD plus VTP but less than VDD or equal to VDD. In this case, nMOS it continuously operate in a linear region and pMOSFET goes into the cutoff. pMOSFET goes right. So in this lecture, we have derived the operating region of nMOS and pMOS in a CMOS inverter at a different input voltage range. Hope you have enjoyed this lecture. Thank you.